This is a lesson on force by an electric field in a unit on electrostatics. To review very quickly properties of electric fields that are relevant for this lesson, we need to note that electric field is represented and adds as vectors, and the field at any point is tangent to that field line. Even if that field line is curved, we will look at the tangent to the line at that point. The lines point away from positive charges and towards negative charges. The electric field lines do not cross and are continuous, so there's continuous values along here. There's no incontinuities. The density of the field lines is proportional to the magnitude of the field. So when we look at these field lines, the electric field is going to be larger in the area where the field lines are more dense. So those are the few properties of electric fields that we need to know to think about the force due to an electric field. The electric force on a charge in an electric field depends on the charge value and the electric field value. So here's the equation here. Notice that it is a vector equation. I noted that on the previous slide. It's a vector equation. And the force is in the direction of the electric field if the charge is positive. If the charge is negative, we get a relative negative sign in here, and the force will be opposing the electric field. So when we put a positive charge in here, that positive charge will be moving force to accelerate along that electric field line. If we put a negative charge in there, that negative charge will move along the electric field line in the opposite direction of the line. So the force opposes the electric field. And this is for any charge in any electric field. I've chosen a net electric field due to 2-point charges, but this could be a constant electric field. You just put a constant value in here. So we're saying positive charges move with the electric field and negative charges move against the electric field. And what I'm going to note about this force, as I would about properties of other forces, is that it acts at a distance. It's a non-contact force, which we kind of know that about positive and negative charges. They never actually touch. They repel or attract one another. And this force is also conservative. So when we think about work and energy, when we get to that portion of this material, we'll remember that the force is conservative. So I just picked a simple example to look at how this equation works, and it's for a point charge in an electric field. It says a small object, which has a charge Q equals 7.5 microcoulombs and a mass is 8.4 times 10 to the negative 5th kilograms, is placed in a constant electric field. So I'm going to note that. That's just a constant value. Starting from rest, the object accelerates to a speed of 2.3 times 10 to the 3rd meters per second in a time of 1.2 seconds. Determine the magnitude of the electric field. So the electric field we don't know, and it is a constant value. We know other things though, and I can write this out. They give me the charge of it, 7.5 times 10 to the negative 6th coulombs. That's a micro. The mass is given 8.4 times 10 to the negative 5th kilograms. And they give me a couple of speeds here, starting from rest. V initial equals 0 and V final equals 2.3 times 10 to the 3rd meters per second. And notice with my V's here, the velocity, the symbol I use is a cursive V. In a few lessons, we're going to get to a large case V, which is going to represent voltage, and so I use a cursive case V in order to distinguish those two symbols, those two concepts and equations. And they also give me a time, and I can write that down. The time is 1.2 seconds. So when I look at this, I'm asked to find the electric field, which is in here. I can write this out. If I know the force, I would multiply the charge by the electric field. And we don't know the direction of the electric field. We just know the force will be equal to that proportionally. And we do have it seems like we do have a positive charge. So then we know that the electric field is in the direction of the force. And I can draw a free body diagram here to represent that. So if I know it's accelerating in this direction and there is a positive charge, then I know the force from the electric field must be in the direction of the acceleration. If this was a negative charge and I have acceleration in this direction and the force is in this direction, then I know the field would be in this direction in the case where it's a negative charge. But because it's a positive charge and the force is in this direction, due to the vector equation here, I know the electric field and the electric force have to be in the same direction on a positive charge. So I have that part of the equation set up. They give me information in here, the velocities and the time, and I'm noticing that I'm looking at forces. So it's very natural for me to think about the acceleration. I drew that in the free over here next to the free body diagram. So let's find the acceleration. I know the definition of acceleration, and you can remember this from your early physics classes, is the change in velocity over the change in time. So I'm going to go v final minus v initial. So I have 2.3 times 10 to the third minus 0 over the time, which is 1.2 seconds. So I can find the acceleration here real quick. It's 1.92 times 10 to the third meters per second squared. So that's an intermediate step in there to find the acceleration. Once I know the acceleration, I can go up here and say, well, the net force due to Newton's second law, the net force on an object has to equal ma. So that net force here has to equal ma. So that's what I'll put here. Ma equals Q times the electric field. I'm solving for the electric field, so I'm going to do some algebra and isolate that. Ma over Q. Now I can plug in values. I know the mass, which is 8.4 times 10 to the negative fifth kilograms. The acceleration I just calculated, 1.92 times 10 to the third meters per second squared. And I will divide by the charge, which is 7.5 times 10 to the negative 6 coulombs. And when you multiply this out, notice you have mass times acceleration on top. That's a Newton. That's force. It's a Newton. Over charge, which we know is a coulomb, and that I recognize as the units of electric field. So when I calculate this, when I run this through the calculator, I get 21,466.6 repeating newtons per coulomb. Or you could represent that also as maybe 21.5 kilonewtons per coulomb, and that would be a perfect way to represent that. So that's how you can straightforward use force equals EQ, and in this case it was a constant electric field. In the next lesson we will look at the electric field due to a point charge.